Alrighty, mic check 1 2. Hey, how's it going, guys? I am live now. It goes live right away now. I was just checking out the Falcon Space program's live stream, and I wanted to talk about a couple things, including some of the things that they just mentioned. And that it's still going now. There's a premiere. We're gonna go live with these guys in a couple minutes. I wanted to kind of answer some of their questions and talk to them live and connect them with my audience and get more on this topic of getting these experiments done and figuring this out. So I'd like to thank Keenan for helping me fix the. He's really good with OBS software. We fixed the issue with the condenser mic, so this condenser mic should be working. Everyone can hear me good, crystal clear audio, all set. Yeah, nice. So 6 people are. I don't mean to be messing up the premiere of this of what they're trying to do over there. I was hoping to get those guys to come on live, but there was a couple things that they were talking about that I want to kind of get together because they were asking for someone who understands this stuff and has some good theories on gravity and what gravity is and how to understand it a little bit better. First off, there's no real official theory of gravity. There's no solid experiment that's ever been done that's really like proven the graviton or figured out like how does actually gravity really work, how to, because we never figured out how to turn gravity off. There's no such, we never discovered anti-gravity. So in order to really understand gravity, we need to basically figure out anti-gravity or how to create anti-gravity, and this has been the topic of the discussion. They recently learned about the Alzaphan experiment, which is related to nuclear magnetic resonance. Nuclear magnetic resonance was discovered by a guy named Edward Mills Purcell, who won the Nobel Prize for the discovery of NMR. And was actually hired after the discovery of NMR. He was hired to head the CIA's Project Rainbow, which was the main project out at Area 51. So a lot of this information has been classified. It's heavily classified because it's related to some really deep classified stuff. Once you start digging into the science and understanding, how these resonances work, what the resonances are, what the different frequencies work with, and how to hack into things on this whole level. So the CIA instituted Project Rainbow to basically map out the entire electromagnetic frequency spectrum from the high frequencies to the low frequencies to figure out all the how different atoms and everything would respond. They took that information and started doing a lot of other, it's been held classified for decades, and now it's like really coming out and more, and is taught more in colleges and is more common knowledge. Before it was just kind of like you learned you learned how to do math, and they drilled you on how to do math and how to be a good mathematician and do like the physics and stuff, and then they brought you into these secret programs and gave you access to some of this other information, which would providing you knew how to do all the math to solve for and figure this stuff out. And then they hoped that it was so complex and complicated that average people couldn't ever get access to it. So that's kind of how a lot of this stuff went. No, but with what you're talking about with Alzaphan, and what they're trying to do with the Alzaphan experiment. So they're in the lab right now down there, and they just sent me this. Let me see if I can't rotate it and look at this. So they got bismuth oxide, niobium oxide, aluminum powder, tin powder, copper powder. So they got a whole bunch of pure metals, including magnesium and bismuth powder, and they were going to try to figure out a way to replicate, some of these other materials that, we would love to take a look at that material that they sent to the U.S. Army instead. But I made a video before talking about their reasoning. Lyndon Moulton Howe said her reasoning behind sending that material to the U.S. Army is they didn't have ability to produce terahertz frequencies to activate whatever was with that material. That's bullshit. I could create terahertz material. If they gave that material to me, I would get the people together to create terahertz frequencies, and we would hit it with that. And like, we still haven't heard anything back from this Army CRADA and this whole dog and pony show charade that I'm convinced it all is. So we're doing the experiments on our own because I'm not waiting for TTSA. I'm not going to team up with TTSA as Steve Bassett wanted us to do when he met with us at Alien Con out in LA. Um, I don't. We're going to do this ourselves, and we're going to do it independently, and regardless of if we're going to get funding or not. The little funding that we have received has been greatly appreciated. You guys are awesome, and you're helping push real science along. Um, but this is going to happen regardless of whether or not we have a $1 million business surrounding this, and we're going to work towards this. Like the Wright brothers built their bicycle shop and created the world's first airplane. We're going to figure out the nanotechnology behind how this NMR, whether it's nuclear magnetic resonance precession, and how it works. So let's talk about this a little bit more. I want to talk about the theories of gravity and kind of how I think it all fits together. So we'll go back to Edward Mills Purcell. He was born a year apart from this other guy who worked on a lot of the top secret projects too. And his name was John Archibald Wheeler. And Wheeler, he worked a lot on unified field theory, and actually, studied and worked under Einstein, I think, at Princeton. And even though he was much younger than Einstein, but this guy was really wicked smart. Did a whole bunch of top secret research. You can get his FBI file and read about some of that. He was a metallurgist and an expert with metals and materials and what's called spintron, like the birth of what's called spintronics, because I believe a lot of this has to do with spintronics. It appears a lot in those in the classified literature when we look into this kind of research. It appeared certainly early on in my metamaterials research, which also Jeremiah called out in this video here on the Falcon Space program page right here. He called out about insiders that had information that talked or had said something and stuff, and hello, I used to know one of those guys, and his channel disappeared, and Bob Lazar took over the scene as being the only guy to come out of Area 51 and talk about the science. But that's not true. Edgar Foucher, if you look it up, you'll just find my channel and a bunch of my stuff. It's like I'm the only source, for information on it, aside from the other guy that Andrew Johnson that Ed ran to when kind of things fell apart between me and him. But that didn't disqualify some of the things that I've never disproved, because I went on a mission to try to debunk and disprove Ed and come together, because he lied about a couple things that we caught him in, and it was just drunk friggin' boasts and talk and other shit that I think that, I don't know, for some reason or another, we caught him in a couple of lies and of other things, and there was other people involved too that I might know a little bit better. We're going to try and I'm actually going to do a 10-year anniversary, because it's been 10 years since we did a lot of the Ed Foucher stuff. I'm going to do what's going on with the story now, and I want to interview some of the people who were involved with the forum that got taken down that we had, and all the stuff that we had put together. Because Ed Foucher was the first person to talk about metamaterials, and I went on a mission to try to debunk this guy when we had this huge falling out, and he doxed me, and that's when alien scientist, I had to come up with my face and my real name. Yes, I'm Jeremy from Rhode Island, and so I tried to debunk Ed, and man, I had a tough time with that one. I found some other references to quasi-crystals and metamaterials, but Ed didn't have the technical understanding to really put this together unless he heard from someone else, and he definitely worked at Area 51. We have the document dump. I dumped a lot of the records on him already, and we have a lot of that stuff together. I'm gonna actually change this part right here. I gotta change some of the stuff. But yeah, we got the FOIAs back, man. We were thinking that it was gonna say he didn't work out there, but sure enough, man, and there was parts of it that were classified, and it was his assignments at that base. He definitely worked out at Area 51. The first person to talk about metamaterials, years before you'll find anything about them in the scientific literature, which starts around 2002, 2004, and then picks up really big from there. But, man, yeah, I do that a lot. I make up songs I could do like you could get someone in the room to come and tell a story, and then I'll do like a cover song, and I'll make up words on the spot about the story that they just said, and I'll make them all rhyme and everything too. I'm pretty funny like that sometimes. Um, Anyways, I want to talk about the friggin' Ed Foucher thing. Ed Foucher was a friend of mine, man, and I'm sorry for burning him because I tried to burn him hard, and he lasted the fire, man. Oh, he's definitely not in the debunk bin anymore. I had him in the debunk bin for a while, trying to debunk the crap out of him, and man, like I said, we debunked the shit out of Bob Lazar, but like this guy, he's the real deal, and they buried him. You can't find nothing about Ed. You find everyone knows about Bob Lazar and Element 115, but no one knows about Ed and that flying triangle and that rotating Mercury engine that I've traced back to a lot of these guys. So Wheeler and DeWitt wrote this equation. It was the Einstein-Schrodinger equation, the wave function for the universe, and kind of coming up with this whole idea of quantum gravity and everything, and it aligns really well with some of the stuff that they were talking about. So coherence in physics. So coherence is a very key subject in physics, and it's definitely key to kind of understanding how everything works together, because it is a way, everything is kind of like this giant wave function, and the universe is a giant system of waves. Everything comes through in waves, and understanding how those waves interact in especially the process of coherence is really key. So this is a good diagram. Waves of different frequencies interfere to form a localized pulse if they are coherent. So you can add, you get a bunch of waves and you add them up, and you can create a localized pulse. And that localized pulse is kind of this way to create this whole wave function. You can basically you can create a localized pulse using waves that extend it for infinitely. You add a couple infinitely extended waves and the right frequencies together, and you'll create a localized pulse. So that localized pulse, you can think of it as a localized vibration, this traveling impulse or something, but it's really built up of a bunch of waves that extend over the whole universe. Kind of a weird way of connecting everything. So everything's kind of connected through this process of quantum entanglement, and it's all vibrating, and it's important. The way to understand quantum coherence is to understand quantum decoherence and quantum scattering. Which really I want to get more involved with Ken Griggs and the team that he's putting together. He's putting a team together to make a software. He was looking for computer programmers, someone who can do the software to build the Phoenix program, so that we can then do calculations using Phoenix. And I assume once we put this all together, that we're going to get it all in one spot together and then publish it. That was Ken's intention, is to get this published. And but we're looking for. I assume he's still looking for the right team to put this together, and I want to set like a ultimatum date that we could kind of set goals for, of getting all this stuff together, because it's important to have that theory on the grander scale. I think Phoenix was a great insight. It's amazing that he was talking about all that stuff with Phoenix theory with me when we were talking about the Wolfram stuff, and then Wolfram came out 2 years later with the Wolfram Physics Project, and now he's trying to do the same exact thing that we were talking about 2 years earlier, the same thing that Ken's been working on for 15, 20 years now, that Ken already has way more ways. I believe that Ken is in some ways way more advanced than some of the stuff that he's coming up with some interesting paths and interesting insights that Wolfram's shown. But a lot of the stuff I think Ken was on to before, and was afraid to show me too many insights into, but because he wants to get the theory published, because what happens is if you share it, someone will steal it and stuff. But I really think there's something more to that, because Stephen Wolfram's talking to Jim Gates, who is Ken Griggs' advisor, and bringing Jim Gates on, and he's talking to all the right people that are involved with this, and Ken has been involved in all the right theory on this kind of stuff from the start. And I want to kind of get into that. What is space-time? There's an article that he wrote called "What is Space-Time Really?" and that was back right before he came out with the whole thing that he revealed it during COVID-19. But this article by Wolfram, it was on his blog, What is Space Time Really? Yes, and this article came out, and I knew that it had to do with this whole idea of coming up with the ultimate theory through creating a network or a code that would chunkify space. It would turn things into chunky space. And so I've been talking to a lot of people who are connected to all this, the right, have all the right connections to all the right people with all the right theory on the right theory of gravity. And I want to put it together to kind of like really figure this out and help figure this out, because I don't know all the material science. I'm not the chemist of the material science. I do talk to some people that are into different things. Oh, that was Bill Clinton. I was finding, oh, Bill Clinton, man, those pictures of him getting the back massage and all the other pictures I found since, man, that was just shocking. Remember, there's the painting of him in the blue dress from the same guy who did this painting. Very curious stuff going on there. I don't want to get into all the news stuff yet before I get into before I finish the thoughts on gravity, because gravity is the key topic, and quantum gravity, the theory of quantum gravity and how to test that is the key here. So I want to talk to the guys in the lab. I've been talking to a bunch of other labs around the world. Who are also working on similar experiments and stuff. So there's a competitor, of course, there's the M Drive, and everyone knows Mike McCulloch and quantizedinertia.com and all his work that he's been doing on Q factor and how to, and then we've been doing some theoretical work on and experimental work on how to increase Q factor. And the shape of we've done a lot of experience with the different shapes of the cavities, and now we're working with different materials to try and get some of the materials down. And we think these layered materials are going to be key, because it's all about increasing that Q factor. If you increase the amount of layers, you're increasing the amount of cavities and the amount of the effect that can possibly go on, theoretically. At least that was one idea. So there's a guy, another competitor out there to the M Drive as well, and I've been looking at all kinds of things like this, talking to all the different groups out here working on this, because there are some problems with the quantized inertia theory that even Mike has pointed out, and just waiting on it explains so much theoretically that there's got to be something more to it, and it needs to be kind of looked at and explored, because there's definitely dark matter is a lie. Man, we know that they've been spending billions looking for dark matter, and we know that it's just like this shot in the dark, this wasted direction. If we had that kind of funding to search for, do these experiments we want to do with gravity, man, we would have learned so much more. But why hasn't any of the funding been for gravity and gravity research? Gravity research gets like no funding in physics, and all this research goes to dark matter and particles and stuff. So it's kind of physics needs to change, and the way the money works needs to change. And the only reason it doesn't change is because it threatens some of the biggest businesses like oil, gas, and of course, airplanes and the military industrial complex, helicopters and airplanes. You don't need helicopters and airplanes if you got this stuff. All right. So I'm hoping that these guys will call in on Skype here at some point. I'm gonna talk a bit more about what's going on with these guys, though. So I talked to an insider who got it, who's in communication with that group, and he's given me some information from inside Emilio Loretti's group, including some of his capacitor designs and experimental data and setups and stuff. So I'm going to get that information over to you guys at the lab there. I just learned about that recently, so I have to figure out how to make that connection with you guys so I can get you that information. Because he's got some interesting experiments, along with what there's a couple people on Twitter who follow Mike McCulloch who do some experiments that asking questions is one of the guys, and they've got some interesting stuff. So Loretti's got a couple different theories, but I have actually a friend who's really smart and knows a lot about this stuff, and I'm not sure if it's his theory or he got it from somebody else, but and regardless, I did not create this theory on my own, but I want to share it because I think it's brilliant, and it's definitely something that needs to be looked at and tested. And he pointed out something called shot noise that I had not, I think I'd heard of it, but I'd never really given it much of a second thought. But shot noise or Poisson noise is a type of noise which can be modeled by this Poisson process, which is actually a combinatoric and additive process, which is very intriguing because that's what Ken Griggs in Phoenix theory says that gravity is. So in any case, the Poisson process consists of points that are randomly located on a mathematical space. So that's kind of what space is. It's a math. You can think of it as a mathematical space, and this Poisson point process is related to how basically space-time connects with itself. So that in an electronic noise, so shot noise, in electronics, shot noise originates from the discrete nature of electric charge. So shot noise also occurs in photon counting in optical devices, where shot noise is associated with the particle nature of light. So there's a connection here where light could also be particle, like electrical. If light is discrete, what if electric charge is discrete and it creates shot noise? Then what if light is discrete? If space-time is discrete, like these quantum gravity theories and these new models would suggest, if space-time is discrete, then also light would be discrete. It would just be the way we measure it that gives us rise to this timekeeping phenomenon that we see in the results of entanglement experiments and the Bell hypothesis and the other different experiments that we've talked about. So the whole idea is that, holy crap, if shot noise creates pixelization and creates an error in the whole message of the way things are connected, if light did the same thing in sort of a 3D lattice that was, space-time, that there would be this loss of information similarly. There would be this shot noise in the model. And if there's that kind of shot noise in the model of this, how would that information loss come out? And how would that information loss be accounted for, error corrected wise, or within the code? And the way that information loss is accounted for is through gravity. And you'll notice that anything affected by photons is affected by gravity. And that when we have, we talk a lot about, the scalar waves and the whole phenomenon of scalar waves, that, additive destructive interference, doesn't account for photon momentum. When you account for destructive interference, if you think about destructive interference, two waves cancel each other out. But both of those waves had momentum going in the same direction. They weren't, opposite. So that it should add. So there's no explanation for where the energy goes. It should go somewhere. It doesn't just disappear. And that's like this whole idea. So the whole interesting thing is it doesn't disappear. It goes into this time domain. But the whole, if you were to draw the Feynman diagram for this, right? The Feynman diagram would look like two photons and a graviton. Okay, it would look like two photons connected by a graviton. Is what it would look like. It would be like the photons would be separated and there would be a graviton in the middle. So the graviton is essentially, if you think about gravity, the graviton is essentially carried by photonic interaction. It's sort of this loss of information in the pixelation of the picture, caused by the quantum chunky space nature of space-time. That space-time is chunky, it's pixelated, it's literally like we're living on a computer. This explains also quantum non-locality, which is the key. quantum non-locality explains why aliens could get here, why those distances aren't so far. So guys, just to sum up what I'm talking about, we got Jeremiah and Mark here live in the lab. They just Skyped in. We've been waiting for this call. Guys, so what do you think about the theory, all this stuff that I've connected, going back to Wheeler and Mills Purcell, who Mills Purcell won the Nobel Prize for NMR. NMR is the basis kind of for the Alzheimer experiment, this whole idea of quantum coherence and this whole idea of coherence. And the idea of coherence can be explained through the idea of a network and these new emerging theories. So I haven't completely thrown out the academic side because there's been a lot of false paths with loop quantum gravity and string theory, which even Susskind admits string theory is pretty much dead. He's like, it hasn't led, it hasn't given us the results we wanted. There's something else going on here. And I think that some of these new theories may be onto something. We haven't quite filled in the whole picture, but the whole essence of the idea is that we live in almost like a computer program. It might be a quantum computer, it might be a really hyper advanced and really fast and amazing computer, but essentially we're software. We're hardware running on software. Like everything is. It's a much simpler model to think of everything as just space. There's no space or like objects and then space. Everything is space, including objects, is just bundled up space. That's kind of like I said. You take this coherence. If you go to that picture I was showing, did you guys see it on coherence?
Can't see your screen. You have to share your screen with us.
Yeah, I'm gonna share my screen with you guys.
There's a big lag, like several minutes.
I know. Oh, several minutes. For me, it's like several seconds.
Oh, there we go.
All right, so let me see coherence. Right, so I was showing this, and because you guys were mentioning coherence and talking about coherent matter, and I was just like, well, what is really coherence? And you got to put quantum in front of everything in order to get the right quantum coherence. So in order to get quantum coherence, there's this interesting thing. It shows a wave packet, right? And it shows it created by a bunch of long waves that extend over the whole universe that create this isolated wave packet. Now, I want to point out that a lot of the math that we do, all right, a lot of the math that we do in quantum mechanics, especially the predictive math, is based around something called the Dirac delta function, all right, and that's a renormalization function that they use to basically project things onto a point in space so that they can get the math to work. So the math could work other ways if we weren't, like we always said that like there's some kind of like errors in the way that we're approaching the math and the way that we're doing the math. And we've kind of identified a lot of those. They're in Dirac's work and what Dirac did for the, his reinterpretation of quantum mechanics. But he was only just showing us that it's got to be something. It's got to be something deeper, I think. And
I like what you're showing me right here. This makes a lot of sense.
so this direct delta function is what they use in a lot of these lot of quantum mechanics. It's an operational calculus in order to project things onto a point in space so that they can get the wave math to work. Because then the wave math works, but they have to kind of project things onto points, and this is kind of how they do it.
Does this basically allow us to take to figure out what the phase conjugation amplitude would be of like several different waves that are joining together, where we're looking for those wave packets, quote unquote, that are generated as a result of crossing nodal points of these various wavelengths? Would this basically allow us to calculate what the amplitude or the frequency would be of that packet?
Hold up, I gotta put. Hold up, let me change your audios, guys. Your audio's not coming through on the stream. I just gotta change that real quick. Shit. So speakers, you guys are gonna go through. Oh shit, I have to do that. All right, hold up a second. I gotta change this around. Sorry, the
It's on his end.
But you can hear us fine, right?
Yeah, he can hear us.
I can hear you guys fine. I just want to make sure you guys are coming through on the stream audio. There we go. I want to make sure everything's set to the same thing. All right. So basically, yeah. State that again, Jeremiah, if you could. We're talking about.
Yeah. So It looks like what this math allows you to do, if you can perform the math at all, which for some of it's beyond me. It looks like it allows you to figure out where these multiple waves have a phase conjugation and what the amplitude of it might be. So if you mix just random noise together, you're going to eventually get some waves that intersect at a given point in space, and where they do, you can have very high amplitude pulses at a single point formed. And I think that's what this is talking about, if I'm understanding correctly. Would you say?
Right. It's talking about like wave pulses, and when we're talking about coherence, so there's a lot of different things to understand, and one of the things is soliton, for example. One of the theories is that that particles are essentially solitons. They're essentially like these envelopes of where this coherence agrees that there's this like there's this packet of energy. This
I could very much see the possibility of that being the source of matter.
Right.
Well, this is all very nice, and it's great to talk about theoretically. What we need at this point is somebody to actually design us a waveguide that can create these interference patterns, so we can try these experiments. Could send the file over on on AutoCAD or whatever. We could print it out on our 3D printer and make it here in the lab. But that's the actual data that we need right now. It's not the math. I mean, that's not really going to help us much. Exactly what you're showing over there. These are the powdered samples that we have. We're going with powder based on the theory that there's skin depth effects at 9.5 gigahertz, which is a very low skin depth in the metal, meaning that the RF field only permeates a little bit into the metal. So we're going with very small pieces, and we're going to suspend them inside of epoxy in order to get this effect. We have aluminum, niobium, bismuth, trioxide, tin, copper. One in the center, that's magnesium. And there's bismuth powder, which is basically bismuth without the oxygen. Iron powder, 2 different versions of iron, and there's cadmium or something like that. Some of these are high spin. Some of them are nickel silver over there.
So you guys want to actually produce metamaterials?
We're making metamaterials, and we need to know from the people that know what mixes to try, and any reason why to try bismuth with magnesium. I was going off of a hint from Linda Moulton Howe's sample that she claimed came off a crashed UFO, and that's what they found.
If we could produce that magnesium bismuth layering in the right way, get enough.
Does it need to be layered? Why does it need to be layered?
Well,
can it just be
on
mixed?
A craft. I mean,
well, if you want to mimic their material as closely as possible, we have to get and I was looking at hydraulic press. You could get a hydraulic press and get sheets of this. If you could get sheets of the metal and just push them in a hydraulic press, you could push it out thin enough where they could get them really thin.
We've been talking for the last 4 days about getting a hydraulic press specifically to press samples together and to be able to form some of these materials.
I have a 30-ton press up here.
Yeah, that's basically what we need. We need at least like a 2-ton press just to start with for small samples, but ideally, it'd be something larger, and we'd have bigger plug sizes, so we could make samples up to 1.5 inches or 2 inches of diameter, maybe even larger. That would be quite ideal, and we could make them thin.
Yeah, does anyone in the audience want to buy? You could buy us one at Harbor Freight. I know there's a Harbor Freight in New Jersey, probably right up the street from your house. We could get one from Harbor Freight for probably let me just check real quick. I know they have them around here.
Or New Jersey's got one and they want to donate it. That'd be awesome.
Or even better, somebody.
That's where my dad got his.
If somebody nearby has a machine shop that's willing to help.
$29. There's one that's $200, or there's another one that's $400. That one's like air powered though.
You don't need something that's like incredibly heavy that's designed to be used every day.
Tool.
Use that often.
Yeah, this one's 12 tons though. It's only
Check if it's in stock here in New Jersey, and I can go pick it up with my pickup truck. And if anyone wants to donate for it.
Yeah, $130, dude. Someone's got that. They can put, that would be awesome for the machine shop anyway to have. It would be better to have a 30-ton one. I don't know let me see what it costs to get this one's a 20-ton. 20-ton for an extra $80. I don't know.
We got a vacuum chamber the other day.
Yep, we just got it in yesterday, actually. We had a chance to hook it up and test it. Built a sample tray for it.
Nice. Yeah, you should definitely try doing some of the layered experiments in a vacuum chamber. I'd be better to do them if you could. Be so the microgravity environment or something. You know what I was thinking is if you just use mechanical vibration, like I was saying, like I have a vibrator tool. I can set the RPMs, and you could vibrate the
Is that your
mold
girlfriend?
in order to shake it at a certain frequency
Yeah.
to stabilize like the
So basically,
positions.
just allows the powder to be compressed more easily. It kind of shakes the air out first. Is what you're saying?
Yeah, just for like the process of like those epoxy makes, because sometimes when you mix epoxy, it gets air bubbles and other stuff in
That's
it, and
that.
that will
Okay.
also shake all the air bubbles out and
Well, you
impurities
can't
in
really
it.
take the air bubbles out of epoxy, but that's why you have a vacuum chamber so you can degas it properly. It needs to be able to pull a pretty good vacuum to expand the volumetric air that's trapped inside to a large enough space where the bubbles can pop, and then you can get rid of them. But yeah, vacuum chamber is a perfect tool for that, and a shaker is a perfect thing for sorting powders and other small particles.
Also, I wanted to mention
Nice. Hey, Nicholas just sent me $50 on here. I got to
So
figure out how to get that money, and I'll send it to you guys for
less
press.
than halfway there. That's awesome.
I also wanted to mention that shaker is also going to be used for one of the experiments to see whether we're dealing with weight loss, gravity shielding, or inertial mass cancellation. Because, like, if you shake the sample while it's in the dynamic nuclear orientation state, then you'd get X frequency
Right.
from the motor, and if it changes when it goes back to a normal state, then you're probably dealing with some change in inertial mass in the inertial mass of the object, which would
Right.
indicate that there's inertial mass effect versus gravity shielding.
So what we basically want to do is use some kind of small transducer, like a piezo transducer, to shake the sample back and forth, and we can measure the amount of power that the transducer draws. And a change in mass will equal a change in power. It will take less power for the transducer to oscillate the lower mass. So if we can measure that very precisely and measure that change, we should be able to instantly indicate that sample's weight loss. But the reason why shaking it is important is because we're also adding momentum. And so even if gravitational mass doesn't change, if gravity is still pulling on it just as hard, but inertial mass changes, at least that method will allow us to detect it.
Exactly.
And then the scale can also, because it's a very fast oscillation that won't affect the scale because it has averaging functions and it has analog filtering, it will still show us a gravitational mass change simultaneously. So we'll be able to see if there's a difference between the gravitational mass and the inertial mass, and if they change linearly or if they don't scale together.
I wouldn't want to try attaching a scale to something that's shaking.
Well, it's going to be, we're talking shaking at 50,000 times per second or more. So it's a very fast oscillation, way beyond the filtering limits of your scale. It won't even make it all the way up the cable that your scale is attached to the sample with.
All right. I was just thinking of using like a phone vibrator type of setup and just.
Yeah, we need it a lot faster probably. If we want to take accurate measurements of the shake. If we just want to shake it, that will work just fine.
I was thinking more like a piston pump sort of thing that just moves it back about half an inch,
That's
back and forth.
a half an inch. Yeah, that's a lot. That'd be a very large amount of motion. I'm thinking
Yeah, a little,
nanometers.
RC motor. We have them
Well, we
here.
could do both. We could do either.
Do you have something that rotates at 50,000 RPM?
No, I'd use a piezo transducer because it doesn't have a problem creating a linear oscillation. It's going to be just like a piston. It's just only going to move, a fraction of a millimeter instead of.
The problem with the piezo transducer is you'd have to connect it to the sample. You'd have to have a way to connect it to the sample, like a rod or something.
You would have to have some kind of way to.
And the
connect it.
piezoelectric effect gets affected by the RF.
Well, the piezo transducer is not going to care about the RF.
It will. That's why the scale was going off.
It's just a chunk of. Well, yeah, I understand that we can shield that too, and we can test it without the sample on there and see if it's affected.
That's what we have to do. Yeah.
There's a way to shield it.
There's always an engineerable trick around every problem, but you got to point out the problems in order to figure out what to do next.
Yeah, so as you guys can see, it's really just an open discussion of figuring out what we can try because we're trying to look for things that aren't commonly looked for. Even trying to detect the difference between inertial and gravitational mass is something that's not really tested because they're assumed to be identical in pretty much every way.
The
But they're
equivalence
not.
principle, yeah. If you could find a violation of that. So this theory of shot noise and quantum decoherence, like that basically light is, you're getting this image and that it's distorted in one direction because of the amount of information, that the earth beneath us has a ton of information there, and that distorts kind of this information in one direction so that that there's a loss of information and it gets filled in by gravity inside That's sort of the model that I'm liking at the present moment, because it connects a lot of these theories of quantum entanglement, and also and it connects a lot of stuff for me. But how would we test that? How would you build an actual device to, some metamaterials are very interesting. There's a lot of stuff. If this gravitational interaction is mediated by photons, is it a specific frequency range? Is there a specific frequency of photons that does it? And what's going on there? So that's what I'm interested in. What did they find when they did Project Rainbow at the CIA and did that whole frequency
I'd
mapping?
like to know what exactly they found. I'd like to know more about Project Skyball too, since it seems to be directly related in many ways to what we're doing.
And that whole mention, I mean, I have been investigating put-offs talk and put-off stuff with the terahertz gap, that there's actually, I didn't know that there was a gap. I'm like, there's a gap in the electromagnetic spectrum, that took me for a loop. And it's almost like, is this another unimpendium? Is this another thing, one of those missing, pieces? But if there's things interacting at this frequency that we can't detect, this could be the gravity frequency, and that might explain why that skin of that, craft is tuned to this frequency, this terahertz gap frequency.
It could be if the whole phase conjugation as the production of matter thing is correct, and you saturate the EM with your, or if you saturate the background with your own EM, then you effectively have added a new wave that can phase conjugate with the previous waves, and you could effectively change the matters of things using those waves. But of course, the frequency bands would have to be close enough to each other where you actually get phase differentials that are long enough lasting and have a high enough amplitude to actually observe effects. And if they're really, really far off, you're just simply not going to see it. Like you'll never notice a 1 megahertz carrier riding an audio signal if you put it through an audio amp. And you'll never notice an audio signal carrying, you'll never notice the audio signal that's actually carrying the 1 megahertz signal if you just measure it on a oscilloscope with a high pass filter. So it's like you have to be able to see both sides, and there is an issue with measuring and producing ultra-fast wavelengths in the light band frequencies. Only thing we have right now is materials that naturally produce those frequencies, but we have no way to synthetically change or vary the frequencies other than using metamaterials. Like a laser, like a DPSS laser, is a fine example of exactly this. It uses a series of different crystals to change the photonic wavelength as a result of phase conjugation in those materials. And so one wavelength enters, it hits itself, and it produces a new wavelength that exits. And that's done twice in a DPSS laser. So we can do it that way, but we would really like to be able to turn a dial and change the frequency, and that's not something that we can do right now.
Right.
Not in that range, not in that frequency range.
That's interesting. So one of the things is I was thinking, right, is that this terahertz gap is dead smack in the middle of the frequency spectrum. And if you were to like take this kind of quantum coherence thing and add up all the frequencies from the top to low, you'd end up with like a point right in the middle of the scale,
You might end up with matter. Who knows?
Well, that's what I mean. What is matter? Maybe matter is that one point frequency that interacts, and that's where all the gravity happens on that one little wavelength.
I'm pretty convinced on a personal level that gravity is a wave interaction, and it's happening at a very, very short wavelength. Short enough, and the reason why I say that is if the wavelengths are long enough, they're going to interact with the electrons and the protons of the things we call atoms in a significant way, and some of those electrons or protons are going to absorb that wave and change its angle or various other things, but there's going to be a strong interaction. If the wavelengths are too short, there won't be a full orbital interaction. It'll only be for part of the electron's orbital that the waves might pass and interact, and this partial interaction could have unusual properties. We'd never see it right now with the equipment that we have. We'd never notice if this wave interacted in a small way, because it wouldn't, over a given period of time, it wouldn't change the properties of that matter. We would have to measure what was happening exactly in that moment, and that's when we would have to apply some other force to see if, say, mass was changed.
I guess that's another reason why dynamic nuclear orientation could possibly work, because if there is a higher frequency than what would interact with the electrons, which are out in a cloud outside of the atom, the core of the atom, you have much higher frequencies. That may be where the gravitational field is actually coming
Yeah, it
from.
could
It
very
is,
well do
it
that.
is those higher frequencies, and by orienting them, you may be able to create a plane where the craft can travel, just like a gyroscope. It'll move freely on its spin and axis, on its spin plane and its axis. So maybe that's what happens with these crafts, because you notice they sort of fly out at 90-degree angles. They're never going like that. They're
Right,
going
yeah,
either
they-
straight up or
Yeah, that's
straight
true.
horizontal.
I'm thinking about all the videos I've seen that looked fairly believable of craft in the sky, and you're absolutely right. They do either tend to go straight along their
Give me
center
the-
axis,
Give me
or
the gyroscope. We could actually give a demonstration of this.
yeah, you could.
And it's going to be hard for anyone to see this, but this is a high-speed gyroscope. It's Precision, made in Germany, and we're using nickel metal hydrate modules to spin it up. And as soon as we get it up to spin, I'll show you something really cool. Basically, I can move it freely along its plane. This is the plane of the spin, and also along its axis. But if I try to change its orientation in any way, now it starts to fight me. So maybe this is what's happening with matter itself, that this is the analogy of a subatomic particle, and the spin might be a little bit more intricate in a subatomic particle, but essentially that's what it is. And when you're moving your hand around, you're changing its Larmor precession, you're changing something in it that gives it that extra energy that we call kinetic energy. And by orienting all the subatomic particles in a craft, what you're essentially doing is you're not removing any energy, you're not even removing any mass, you're removing relative mass. Because to change the orientation of the craft will take the amount of energy that it would take to move it if it wasn't dynamically oriented. But if you want to move it along the plane of the craft, or the plane of the spin, or along the axis of the spin, you're free to do so without any interference from whatever fields normally interact that create the kinetic forces.
Yeah, that makes a lot of sense.
Jeremy,
So-
what do you think of that?
I think about that in terms of like degrees of freedom, where in that case you said translation is allowed, but rotation is not allowed. That's kind of what's happening in a gyroscope, right? So we can have translation, right? So translation is moving from one point, that's moving up or down or around. But rotation, that's where you run into problems, is with rotation. So you basically by locking it in with rotation, by rotating it, you've locked it into one reference frame, which has limited one of your degrees of freedom. So
Exactly.
Your rotational degree of freedom.
Yeah, precession is a very, very strange phenomenon. It's one of the most anti-intuitive parts about gyroscopic dynamics that trips most people out. That's what was it? That's I think what got Lathwaite, not Lathwaite, not Lathwaite. Who's the guy that got bumped out of the academic community for claiming that gyroscopes had unusual properties when moved in certain ways? Trying to remember that guy's name.
So I think this is super important to understanding the quantum physics of how this works too, because it's degrees of freedom in statistics, because it's a statistical treatment is what we use for quantum mechanics, but degrees of freedom in statistics can be thought of as basically your dimensions, or the amount of, the different independent basically linear analysis you have to use. You have systems of equations and stuff you can use to basically create a model for degrees of freedom. But with what's interesting about degrees of freedom is that there's a whole theory about and a model for phases of matter. So the phases of matter: gas, liquid, solid, right?
Well, basically, what you're kind of talking about here too, and related back to gyroscopes with the horizon theory, the idea that information horizons exist and that you can only communicate in one direction from where you are, but other information can't be communicated back to you because you have some differential velocity between you and whatever signal you might be receiving. If you look at the angular momentum of a gyroscope and take a look at the fact that around the gyroscope atoms moving much faster, there is a virtual axial information horizon whose position has been shifted as a result of the RPMs that the gyroscope is spinning at. It's not an acceleration phenomena. It's just simply a static velocity or angular velocity phenomena. So it could explain some of the interactions.
Definitely. What I back to my whole thing about this solid liquid gas phase. So like it's all about degrees of freedom. It's saying that when you're in a solid, you're locked into a point. You really can't move around with relation to what's around you because you're in a lattice. So that you have no like 0 degrees of freedom, and that when the ice cube melts, those molecules gain a rotational degree of freedom. That's the first degree of freedom that they get. And when they're allowed to rotate across each other, they can actually move around. So the solid's kind of stuck together, right? The liquid's kind of stuck together, but it rolls around itself. These things aren't locked in a lattice. They're now able to roll. Now able to roll. So that's why the fluid can flow. You can essentially think of a fluid as a bunch of like all the atoms rolling as like tiny balls. You know what I mean? But they're all kind of stuck together because there's surface tension in fluids and stuff, like a solid, but they're not quite fully, intact. And then as you move to gas phase, they gain that translational degree of freedom where they actually can move around in the air and don't have a definite space with respect to one another. So they're not stuck together. They're not like there's no surface tension in gases. Very interesting for the person that observed that it's degrees of freedom that's creates these phases of matter. What we experience in the math, on the macrocosm world is these quantum effects. These are the quantum effects that are causing its symmetry and its degrees of freedom. Again,
Specifically, simply saying that it's temperature.
It is temperature. Yeah, temperature is very important.
Temperature is the base, and then the degrees of freedom is the explanation for why temperature has an effect.
Yes, but also notice that like different things have different melting points. So the temperature, might be, one thing might be solid. The glass that holds your cup of water, if you heat that to the melting point of glass, the water turns to gas, and then
not exactly. The melting point of glass might be like 1 degree Kelvin or something like that. Glass is technically a liquid itself.
Yeah, it's a bad example. It's a very slow-moving liquid.
It has 2 melting points. Then,
that's what I was trying to get to. Is that not everything really goes solid at any point?
Yeah, I know. Matter is a funky animal, but it has these certain kind of behavioral statistics. So what's the next degree of freedom? So if we want to create a degree of freedom beyond a gas, right? There's a plasma. It has this other kind of electrical degree of freedom where they're superconductors,
Almost superconductors.
Almost superconductors, where the electric charge can flow more freely. And what if there's other, if you gain other degrees of freedom, what would those be, and what might those unlock in terms of physical matter and phases of matter? Very, very interesting stuff. I was doing some research on cavitation too, and the pistol shrimp and all that stuff again with
area to look into.
Sonoluminescence. Very cool stuff. So, and this is kind of related to that Tic Tac pattern, which I've been digging into a little bit more too. It's a phononic thing. I had messed up. I had said that it was polaritons and excitons. That's a little bit different actually. It's phonons, and the phonons or mechanical vibrations are so strongly that they cause a polarization of the vacuum, and they can create this production of antimatter
That's
effect.
related to what I'm looking into. Can you have you found in your research what the mechanism for producing the phonon vibrations is?
Other than parametric oscillation, I haven't heard much about that.
How are the phonons initially being generated and controlled?
By a parametric oscillator.
This must be a device that I...
Optical parametric oscillator. This is, I believe, how they're being controlled, according to some of the scientists I've talked to. So...
Another thing we need to look into for this upcoming experiment is something called the hyperfine coupling. That's the connection between the outer valence electrons and the core of the atom. And I've been doing some research online. It's pretty hard to find a chart with the hyperfine coupling for all of the materials that we have. And I was wondering if you could help out with that. That would really give us some basis to stand on to know what to expect with our experiments and possibly what materials to mix with what. That's really what we're looking for right now. I'd love to continue chatting. We need to get back to the lab. Jeremy, I sent you over a list of all of the materials that we have.
Yeah, I'm gonna see what I can come up with. I'm gonna talk to some of my material scientist friends. I'm
That'd be awesome.
basically
You're talking to them right now. They're listening to the chat, and I'm sure there's people
yes. There's
in
people
your
that know
chat.
some stuff.
There are insiders that watch your show. I know this for a fact because I got many great recommendations in the comments. So if anyone's down there who knows anything about dynamic nuclear orientation, put the list that I gave you in the description, and they will opine and give reasons as to why they want to do one thing or another, one mix or another. And if it makes sense, we'll try it out. And we're literally geared to set this up for tonight. So
All right, cool. Yeah, guys, let's keep it short and simple, and I'll conclude that, and we'll touch base in later tonight. I'm gonna send you some more information, and I'm gonna have the right people get in touch with you and see what we can come up with. All right.
Okay.
Thanks so much.
Take it easy.
Thank you.
Falcon out. All right, guys, that was cool. So I'm sharing some of the information I've got, and I thank the people that post this stuff in the chat because I do go back and read these things from time to time, and this is stuff that people have shared, and I've taken note of it, and stuff like that helps, and contacting us helps, we're definitely pulling a team together to come up with some great ways to test these theories and stuff. So I had some more news that I wanted to go over real quick. With the terahertz gap, we talked about all this stuff. There was some news articles I wanted to get to real quick. Oh yeah, this really cool. They found this underwater, submarine entrance where they caught subs going in and out of it, and there's a whole article on it by Tyler Rogaway on the Drive right now. That is really cool. It's like some James Bond type shit, man. Really, that's freaking. There's definitely like some big complex under here that thing goes into. I bet you. That's nuts. Anyways, I'm sure we got stuff like there's other stuff like that we don't even know about too, like in other places, man. That doesn't. It looks like all top secret, but some of that stuff's based on a lot of real, some real stuff too. The secret submarine bases and stuff. But anyways, yeah, some cool stuff that we've pulled together. This whole idea of quantum coherence and quantum decoherence to explain, different theories of gravity. I got a whole bunch of theories on gravity. We're testing a lot of the stuff. Oh, I wanted to see what Daniel Kaplan was doing real quick. See if there's any updates from him. He was this guy right here. He was doing a bunch of cool experiments on muons and anti-muons. Anyways, I'll have to write him an email and see what he's doing, get an update from him, and also the Medio Loretti's team with the PNN that I was kind of talking about earlier, and also quantized inertia. Really cool stuff. Quantized inertia with Mike McCulloch. And man, so many cool people, so many cool groups. I want to get those guys on and interview some of those people soon and talk to them. If you know anyone, have them get in touch with me. We have, of course, so there's a lot of people working on this kind of stuff internationally. We've talked to from time to time, but we're trying to set up this lab down in New Jersey and get some serious funding for the experiments. Well, not funding. We could fund it on our own, but we're trying to get some serious momentum behind this so that we can test some things and get some good information and insights. All right, I'm going to end this right now. I'll thank you all guys for watching, and we'll tune in soon. I'll have another update shortly.